Okay guys, we're going to start Unit 1, which is all about analyzing data, learning all about the different types of data, how you analyze the data, and that kind of thing. So we're going to start by exploring two different types of data, categorical data and quantitative data. And you can kind of see from the names that there's some information there. Categorical data will place an individual into one of several categories. That kind of makes sense. So it's not something numerical per se, it's just whether someone has brown hair, blonde hair, blue eyes, brown eyes, that kind of thing. Those are categories. Quantitative will take on, so takes numerical values for which it makes sense to take averages. So always ask yourself, does the data lend itself to finding the mean or the median, that kind of thing? Categorical data will not. Quantitative data will. It will make sense to do that kind of thing. You always do want to start by asking yourself some questions, and you learned about this in your summer work. You want to basically think about what is the individual, or who is the individual, or what are the objects that are being measured. So you kind of need to think about it on an individual level, what is being looked at, and then what is being measured. So we'll just say who is being analyzed or looked at. You can kind of think of it like that. And then also what, more specifically, is being measured. And these are the kinds of questions that will help you answer multiple choice questions that are kind of in depth and that kind of thing. So who is being analyzed and what is being measured. So let's just dive a little deeper. Do we ever use numbers to describe the values of a categorical variable? Do we ever divide the distribution of a quantitative variable into categories? So let's kind of explore this. Categorical variables can be numbers such as zip codes. So zip codes are categories based on where you live. Favorite foods, and I'm just giving some examples. There's many, many examples here. Hair color, etc. So quantitative variables, some examples for that might be home values, and those home values could be subdivided into, say, for example, low, medium, and high value homes. Okay, so to answer the question, do we ever use numbers to describe the values of categorical variables? Yes, you can. So it's not that categories can never be numerical, but it would be whether it makes sense to actually take an average of those zip codes. That would not make sense to take a set of zip codes and average them. That would not make sense at all. So in that case, that is your clue that it is not a quantitative variable. Even though it is a number, it is a categorical variable. And then furthermore, do we ever divide the distribution of a quantitative variable into categories? The answer here is also yes, we can. And then basically what was a quantitative variable becomes a categorical variable. So kind of just take a second and think through that information. Alrighty, moving along. What is a distribution? You will hear this term a lot. A distribution tells us the values, and it can actually be in words or it can be in numbers. But it's a description that the variable can take and how often it takes those values. So a distribution could just be, for example, if I look at a set of, say, the Unit 4 test scores, and I looked at that distribution, it would tell me all the different scores that I got, and then I would know how often I got certain scores. And that's a good point to make here at this particular time is if I'm looking at test scores, that is a quantitative variable. But if I look at the A's and the B's and the C's, that sort of thing, then guess what? Then it becomes a categorical variable. So another good example of how the two different types of data can kind of blend together. Let's do an example here. So we have U.S. Census data. Here's information about 10 randomly selected U.S. residents from the 2000 census. Okay, so we have all of this information. We have state, number of family members, age, gender, marital status, total income, and travel time to work. All of these are variables about the 10 individuals. So each individual, so I could say like this is individual 1, 2, 3, that kind of thing. Or they might even have a name, Sam, Paul, Amanda, etc. But the information is about those individuals. So who are the individuals in this data set? And that would be the 10 randomly selected U.S. residents from the recent census. So that probably makes sense to you guys. So what variables are being measured? Identify each as categorical or quantitative. In what units were the quantitative variables measured? So the categorical variables here are going to be state, gender, and marital status. The quantitative variables are the number of family members, age, and that would be in years. Now I don't need a unit for family members because you're actually just looking at the number of those. And then income, which is in dollars. And you would think that's self-explanatory, but you do need to give that information. And travel time, and the time is given in minutes. So this is the level of detail that I'll be looking for, and on the AP exam, they will also be looking for. So be sure to provide units when mentioning quantitative variables. So let's look at the individual in the first row. So I can kind of go back up here and just kind of look at this person. And it is not Sam. I just gave that description there. But the individual, in fact, is female, but that could be a female name, who is 61 years old, has 2 family members from Kentucky, married, has a total income of $21,000, and it takes about 20 minutes to get to work. So let's just kind of write that down. So this is kind of the level of detail we'd be looking for. The individual is a 61-year-old female. Oh, and I meant to say married. So anytime you can kind of put it all in one sentence, that's even better. Married female from Kentucky. With 2 family members in her household. And you could actually try to get all this in one sentence, but 2 is fine here. So she has a total income of $21,000 and drives 20 minutes to work. Now, what is this telling you about her? Well, it tells you she's a little bit older, where she's from. She still has 2 family members in her household, you know, her income and how long it takes her to drive to work. So there is some information there, depending on what you're trying to study or do, that might be useful. All right, moving on. Okay, so what is the difference between a data table, a frequency table, and a relative frequency table? So these are kind of the three things we're looking at here. When is it better to use relative frequency? And then we're going to talk about an example on page 8 of the book. Okay, so a data table has individual rows or has rows and columns. And if you want to think of it like this, the rows, there's one row per individual. That kind of helps you think through everything. And the columns, it will be one column per variable. That is a data table. Okay, so we just looked at a data table. The table that we just looked at with the 10 U.S. residents was a data table. A frequency table is going to present, and put a little S there for our grammar, it presents counts by category. So it is still a table, obviously they're both tables, but it's going to show you how many individuals fall into each category. And then a relative frequency table presents proportions or percents. Okay, when I say proportions, it might be, for example, 0.21. Percents would be 21%. That's all I'm talking about there, okay? Whereas a frequency table is going to actually give you the number of the individuals that fall into that category, okay? So I do want to look at page 8 in the textbook, just to kind of show you this. So if you want to open up your textbook kind of in another window, that might be a great idea. And I'm going to put this up here for us real quick. Okay, so this should come up in just a second. And this is a really good example of comparing the different types of data that you can get. So here we go. Let me kind of zoom in a little bit. Okay, so this is an example of a frequency table right here. Let me zoom in a little bit more. And you can obviously get in your book and look at it too. So, okay, so we have a frequency table that shows a radio station and basically the count of stations that fall into each of those types of radio stations. So that is a frequency table. Then that same exact information is taken and converted to a relative frequency table, and here it's presenting the percentages. So that's what's happening here. Basically, you would add up all of the radio stations, get a total, 13,838, and then for your percentages, you would just do 1,556 divided by the 13,838, and that would give you the 11.2%. So I kind of just wanted to show you that, basically showing you the difference between what a table is, or a data table is, versus frequencies and relative frequency tables. All right. Okay, so let's continue on. Okay, so what is the most important thing to remember when making pie charts and graphs? Why do statisticians prefer bar graphs? So here's a little bit of information. You must make sure the graph communicates the data with proper labels and scales. You should always plot data that you're given and show labels for each the x and the y axes, as that's what you're doing. And then of course you want to have appropriate scales where you can communicate what the data looks like with the graph. That's the whole point of the graph, is to communicate what the data really looks like and what's going on in the data. Bar graphs are easier to read and analyze, because it's easier to compare the different distributions. So that's why statisticians prefer those. Comparisons are a little bit easier to make. They provide more information. And as you do some of your homework problems, you'll begin to kind of understand that. So when is it inappropriate to use a pie chart? When is it useful? So you cannot use a pie chart unless you have 100% of the distribution. So it's a case where you would have to have all the information, and it's basically a population or a sample, whatever it is you're looking at. Usually it's a sample, and you know which category all the individuals fall into. You'd have to have that kind of information. And pie charts are useful for displaying distributions quickly and easily. Okay, but it has to be the entire distribution. So what are some common ways to make a misleading graph? This is kind of new to AP Stats. This other stuff, you know what a pie chart is, you know what a bar graph is, that kind of thing is just review. So we will look at this. The first one is something called the area principle. Area should represent the proportions. So area should represent the proportion. So let me just give you a quick example of what I'm talking about here. So basically, if I have a graph, and say I have, and I'll just make up something, let's just say score on last test. And this is not going to be true, but let's say we have some with in the 50. That's not true, obviously. And then we'll go to 60, 70, 80, 90, that kind of thing. Okay, so, and I'm literally just making this up, guys. I haven't even finished grading that test. So let's say we have this here, and then most everybody made A's, hopefully, okay? And then this could either be a count or it could be a percent. I'll go with percent over here. Basically, you want the area of each of these bars to represent the proportion or the percentage of students who fell in that range. So that's what that means, and you always want your bars to be equal width here. So that's what's important, okay? If all of a sudden I made the 90 twice as wide, then this area right here would no longer represent the probability or the proportion, if indeed this was true over here for whatever percentage it is. So hopefully that makes sense to you, but you definitely want, I'm going to erase this part of it, you definitely want your bars to be even or equal widths. So then the height is the only thing that's really changing, and then you have basically the area principle where the area represents the proportion. So that's what's going on. The next thing is using 3D or graphics almost always leads to a misleading graph. But like I said, you do need bars of equal widths, and when you just use the same graphical, I'll show you this in just a second, it's hard to make it larger, like taller, for example, without making it wider as well. So that's kind of what the problem is. The other one is if you don't start the axis at 0, it can sometimes be very misleading, and it will have more impact on the bars that are already really small. So it has more impact on the area for smaller categories with less number or less proportion, depending on what you're doing. Remember that all of this, the y-axis here basically can be numbers, it can be percentages, or it can be proportions, which is really just like probabilities. Okay, so I can have the number of, the percent of, or the proportion. And if you have, if you're using percentages, obviously the area of each of these, if you add them all up, should equal 100%. Proportions, you would add them all up and you would equal to 1 for all the possible outcomes. And then the number would just, if you add them, it would give you the number in the total distribution. All right, so here's an example. What is wrong with the following graph? So this is a case where this height is supposed to represent the proportion that fall into each of these three categories. But because the width is not the same for all these, like if I were to make this the width here, same here, and this would actually need to be a little wider, then you could actually have a representative graph, or a graph that wouldn't be misleading. So that's what's going on. So basically it is misleading since the proportion of number of channels is not represented by area. So it makes it look like a huge drop off, and it's really only 95 down to 81. So the area is not representative of the proportion. So that's kind of the biggest thing here. The proportion is not represented by area. Okay, you are going to complete assignment number 1 in your spiral notebooks, and make sure you have the notes finished for the front and back here, and hope you have a great weekend.